She's slowly starting to feel everything.
Is it her right leg? Right.
Okay.
Well, looks like her and that mom will be twins.
Oh, really?
Forced into the right side.
Okay. So this is, we've talked, at the end of last year, we did a little bit of talk about end behavior and about the bins, there we go. The bins in a polynomial function, and the bins versus the degree and all that stuff. We did that at the end of last year. So this is kind of review and very simple. So f of x is a cubic function that asks for the left end behavior. That just means what's happening on the left side of the graph. So what's happening? It's going towards negative infinity. It's falling if you're reading it backwards. So that's the only thing about this, is that we've always read graphs from left to right, and you do read a graph from left to right. But when they ask for the left end behavior, they want you to read it backwards. So the left side is falling or headed towards negative infinity. So the way you're going to write that is as x approaches negative infinity, meaning that we're reading to the left, f of x is approaching negative infinity. And then when it asks right end behavior, we're starting in the middle and we're reading from the middle to the right, just like normal. And that would be as x approaches infinity, because this is going towards infinity, so we're reading to the right. In this case, what is f of x doing? It is. F of x is approaching infinity. Okay, so then for this particular cubic function, then they asked me what my zeros were. Let's see, looks like I'm just going to read them from left to right, so -2, -1, and 1. And remember, it's a cubic function, so it has 2 bins. Your number of bins is always 1 less than your degree. So then there's the quartic function. Now, this is kind of a strange looking quartic function. A lot of times your quartics are going to look like W's. They have 3 bins. 1, 2, 3 is where these bins are. But when it looks like a W, it's real obvious. There's the 2 at the bottom and the 1 in the middle. So this is a quartic function. Left end behavior. As x approaches negative infinity, so we're reading from the middle of the graph to the left, what is your graph doing?
F of x approaches infinity.
It does. F of x approaches infinity because it's rising this time. Right end behavior, as x approaches infinity, f of x approaches. If I read from the middle to the right, it also approaches infinity. And my zeros this time looks like -2.5. So -5/2, that's the same thing as 2.5. And 2. And that looks like all the zeros that I have. Now, how many zeros should I have?
3.
Quartic.
4.
4. So, and you do, but we'll figure out in just a minute why you can't tell that there are 4. About to talk about that. Okay, last one over here is quintic. So quintic is to the 5 degree. Quint is 5. So you can tell it's got 1, 2, 3, 4 bins. So the 4 bins show you that it's quintic because it's always 1 less than the degree. As I read this graph, left end behavior. So as x is approaching negative infinity, so reading from the middle to the left, what is f of x doing? It is going to negative infinity. And as we read from the middle, so the right end behavior, as x is going to infinity, moving from the middle to the right, what is f of x doing? Positive infinity. And if you remember, on all of your polynomial functions, odd polynomial functions that have an odd, I shouldn't say odd because that means origin symmetry, that have an odd degree. So cubics, quintics, to the 7th degree, to the 9th degree, they're always going to have 1 up, 1 down. Anything that has an even degree is always gonna have 2 up or 2 down, depending on what your leading coefficient is. So quintic, see it's got 1 down, 1 up. Cubic's got 1 down, 1 up. If it was to the 7th degree, it would have 1 down, 1 up. So just a reminder. Okay, so my zeros, looks like x equals -4, -2, 2, and 5. Now I should have 5.
But you have a double root.
Very good. You've got a double root right here. You can
Which is
tell
still
easily
5.
that this one is a double root because it touches in turns. So you really do have 5. Alright, so now that's where we're going, is to talk about when we have multiple roots, or what they call multiplicities of a zero. So multiplicity is the number of times a factor is used in a polynomial. So if you think back to the notes page that we did yesterday, the last problem on the page, you remember we synthetically divided by 1? We actually synthetically divided 4 times, but 3 of the times it had a remainder of 0, because 3 times it was a factor. So for that polynomial, that factor had a multiplicity of 3. It's however many times that factor is used. The only way we're going to know that is to put it in factored form. So in the graph of f of x, the first one, all of these have a multiplicity of 1. See, it was cubic, which means we needed 3 zeros, and we found 3 zeros in this one. So they're right there. In g of x, that's the middle one of them has, so we should have been, it was quartic, we should have had 4 zeros, but we only found 2. But if you look at it, do any of them jump out as being double roots?
No.
What would it look like if they were double roots?
It would touch.
It would touch and then turn around, or what we call bounce. It would touch and just turn right around. Neither of these are double roots either.
It's a triple.
So one of them is a triple and one of them is a single. Anybody know which one's which?
Triples to the farthest root.
This one is a triple root, and this one is a single root. Because anything to the first that's to the first degree, a single root like that, passes directly through. Just like these did. It passed through, and it eventually turned, but it passed straight through on all of those. This one passes straight through. This one is to the third because it does pass through, but it has a little bend right where it passes through. And you can see down here at the bottom, it explains the 0 of -2.5, or I wrote it as -5/2, has a multiplicity of 1, and x equals 2 has a multiplicity of 3, because it has that little bend in it. Now it's still passing through. If they have odd multiplicities, 1, 3, 5, 7, it's going to pass through. But the little bend in it lets you know that it's not to the first degree. Okay, so then in h of x, this one passes through, so that one's to the first degree. This one passes through. This one's a double root, and this one passes through. So that's 1, 2, 3, 4, 5. So that makes up all 5 of the roots that you need. All right. What do you notice about the sum of the multiplicities of the zeros and the degree of the function? They are equal. Your sums of your multiplicity should equal your degree. The behavior of a graph as it approaches a 0 whose multiplicity is 1, the graph passes through. The behavior of a graph as it approaches a 0 whose whose multiplicity is 2, or what we know as a double root, touches and turns or it bounces. And the behavior of the graph as the graph approaches a 0 whose multiplicity is 3, it passes through with a bend. Now, what this is going to help us do is identify all of this is leading towards solving polynomials. And I've said before, and you know from just previous class and stuff, that the fundamental theorem of algebra says that whatever this degree is, that's how many solutions there are, how many roots that you have. Well, identifying all of your roots, it is helpful to know if you have multiplicities greater than 1, because you don't want to keep looking for roots when you've found them all already. So that's what this is all leading towards. So it says we are going to identify the 0 associated with the factor. So they've given us one of the factors. Then they want us to synthetically divide to determine how many times that given factor is a factor. And then identify the multiplicity associated with the factor. Now, you should be able to identify it by looking at the graph, but you're not always going to have the graph. And I don't know if y'all have noticed this yet, but actually these calculators are much easier. But sometimes you can put a polynomial, it really would happen a lot with the 84s. You can put a polynomial in your calculator, and when you hit graph, all you would see would be like straight lines going places. And you would like try to zoom the window and fit it, and you couldn't ever see the polynomial. Because sometimes they're just too big. Now, the Inspires are a little better because when you say zoom fit, they're pretty good about putting it in the window so you can see it. But we couldn't always do that. So, and sometimes you won't have a calculator because I've taken it from you. Okay, so if x plus 1 is the factor, what's the root? Negative 1. So I'm going to write it as x equals negative 1. We're going to synthetically divide. Make sure that you have all of your coefficients, or add a placeholder if you need it. Now, it should have worked the first time because they said it was a factor. But they want us to do it again and see if it's a factor more than once. Nope. So this time, what's the multiplicity of this factor? 1. It only worked one time, so the multiplicity is 1. And you can go look at it. The factor was negative 1 right there. It does pass through. The behavior of the graph, it passes through. All right. Okay, so you can tell by looking at the graph what should happen. Should have a multiplicity of 2. But let's check it just to be sure. Okay, so it worked the first time. It worked the second time. I went ahead and tried it a third time just to be sure. It did not work the third time. So it has a multiplicity of 2, touches and turns on the graph. factor of x minus 1, so my root is 1. Okay, so I used my 1, synthetically divided, got a 0, did it again, got a 0, did it again, got a 0, did it one more time, finally did not get a 0, so it worked 1, 2, 3 times. So my multiplicity is 3, and you can tell right there at the root, at 1, it does pass through with a bin. Okay, so it says, now let's consider how we might be able to locate the zeros of a polynomial function numerically. Consider this function, there it is, that we investigated earlier, and whose graph is shown below. Find each pair of function values in the table below and answer the questions that follow. Okay, so find h of -2 and h of -1. There's two ways you can find it. We could either plug it in, or you can synthetically divide and get the remainder. It's up to you. Since nobody said you couldn't use your calculator, why don't we just plug it in for right now. Now, if this was a non-calculator test, that would be up to you. If you felt like you could do this, cube -2 and then square -2 and all that stuff easier than you can synthetically divide, then do that. Do whatever it's going to take to get the right answer. Or if you're real picky, you might do it both ways and see if you get the right answer both times.
When you synthetically divide, would the answer be in your remainder?
The remainder is your answer. I definitely have had students that would have definitely done it both ways to make sure that they got it right. I got -9 for -2. Did y'all get -9?
Yes, ma'am.
Okay. 9, and 4 on the first two. Did I get that? Yep. Okay, and on the second two, I got 3 and 7. Yeah, okay, just making sure we're right. Okay, so from the graph, you can clearly see that there is a 0 between these two numbers, between -2 and -1. Between -2 and -1, you can clearly see on the graph. But let's say we didn't have the graph. All we had was the table, or all we had was this set of ordered pairs. What shows you in those ordered pairs that there's a 0 between those two numbers?
Those negative positive.
It goes from negative to positive. In order to go from down here, from negative to positive, it has to pass through 0. There's no other way that that can happen. So the y values go from negative to positive. Okay, so, and that's called the intermediate value theorem. We talk a lot about it in calculus, but it just shows that in order to get from here to here, there has to be a number in between. Now, does the same reasoning hold true for the 0 that exists between 0 and 2? We can look at the graph and see that there is a 0 between 0 and 2. There's one right there at 1. But if all you had was this information, is that enough for you to say that there's a 0 there? No. Not without the graph. You wouldn't be able to identify it. So, no. This time the y values are both positive. If they were both negative, the result would be the same though. We wouldn't have enough information to say that there was, in fact, a 0 between them. So based on what we've just seen, what inference can you make about the existence of a 0 of a polynomial function if you know the value of the function at two different x values? If the y values change, if they change from negative to positive, or vice versa, positive to negative, it doesn't matter which way the y values have to change. Then you can determine that there's a 0 between the two x values. But just because the y values don't change, that doesn't mean there isn't a 0. So you can be definitely clear when there is one, but you can't definitely say that there isn't one. And we just saw an example of that. Okay, so they've given us a table of values. It's a quartic function. The function has a next. So just so you know, when they say that, when they give you this information, the value below represents a quartic function, this is not all of the values. They just gave you it's just like pulling up the table on your calculator, and if we could scroll left and scroll right, and there would be more. This is just a little snippet of the table. So it's not a discrete function, it's actually a connected quartic function. Okay, the function has a -0 and 3 positive zeros. Answer the questions that follow. So you can find your zeros. How do I know that there's zeros when I'm looking at a table?
Because you can see them.
How can you see that?
Because the Y values go from negative to positive or positive to negative.
Because the y values are going to go from negative to positive to negative. Okay. Is or are any of the zeros of f of x specifically identified in the table? They mean, can we actually look at the table and find any of them?
Yes.
Which one?
X equals 1.
X equals 1. And how do you know that?
Because f of x equals 0.
Because f of x is 0. So yes. All right, now, what is the multiplicity of that 0? And how do you know?
Because it's negative.
Good. On either side of that 0, it's negative and negative, which means that this comes up, touches it, and turns right back around. So the multiplicity of that 0 should be 2. The multiplicity of 2 because the y values on either side are negative. Meaning the function bounces. Between what two x values is the negative 0 located?
Negative 4, negative 1.
Somewhere between negative 4 and negative 1. And then between which two x, so now we've identified 3 of the 4 because we had the double root, and then we just identified the negative root. So now it asks between which two x values in the table is the second positive root located? 3 and 5. Between 3 and 5. You also cannot assume that just because it's between 3 and 5 that it's at 4. It could be at 3.1 for all we know. So just all you can identify is what two values it's between. Is everybody okay? Anybody have any questions?